Generative AI refers to a class of machine learning systems designed to produce new content that resembles data they were trained on. Instead of simply classifying inputs or predicting numeric values, these models learn the underlying statistical structure of data and use that knowledge to synthesize text, images, audio, video, code, and other modalities. At a technical level, generative systems are learning probability distributions over complex, high-dimensional spaces, and then sampling from those distributions in a controlled way. To understand how generative AI works, it helps to start from the perspective of probability modeling. Suppose we have a large dataset of examples drawn from some unknown real-world distribution. The goal of a generative model is to approximate that distribution as closely as possible. If the model succeeds, then drawing samples from the model should produce outputs that look realistic because they follow the same statistical patterns as the original data. This framing immediately reveals that generative AI is fundamentally about density estimation, likelihood modeling, or implicit distribution learning, depending on the specific approach. One of the simplest conceptual examples is language modeling. In this setting, the model is trained to predict the probability of the next token given the previous tokens. Formally, the joint probability of a sequence is decomposed into a product of conditional probabilities using the chain rule. By learning these conditional distributions, the model effectively learns the distribution over entire sequences. Generation then becomes an iterative sampling process. Start with a prompt, repeatedly sample the next token from the predicted distribution, append it to the context, and continue. The success of modern generative AI, especially in text, is largely due to transformer architectures. These models use attention mechanisms to allow each position in a sequence to dynamically incorporate information from other positions. During training, the model processes large amounts of text and adjusts its parameters so that its predicted next token probabilities match the empirical distribution in the training data. Over time, the model internalizes statistical regularities of language, including grammar, style, factual associations, and even some forms of reasoning patterns. Training generative models typically involves maximum likelihood estimation or closely related objectives. In maximum likelihood training, the model parameters are adjusted to maximize the probability assigned to the observed training data. This is equivalent to minimizing cross-entropy loss between the model's predicted distribution and the empirical distribution. Because exact likelihood computation can be difficult in some model families, alternative training objectives such as variational bounds or adversarial losses are sometimes used. Generative AI systems can be broadly divided into several major families. Autoregressive models generate output sequentially, one element at a time. Variational autoencoders learn a latent variable representation and generate by sampling from that latent space and decoding. Generative adversarial networks train a generator and discriminator in a competitive setup. Diffusion models gradually denoise random noise into structured samples. Although these approaches differ significantly in mechanics, they all aim to learn the data distribution in some form. Autoregressive models are perhaps the most straightforward to understand. They factorize the joint distribution into a product of conditionals and model each conditional directly. Their main advantage is stable likelihood-based training and high-quality sequential generation. Their main drawback is that generation is inherently sequential and can be slow for long outputs. Large language models and many modern sequence generators fall into this category. Variational autoencoders introduce the idea of a latent variable that captures underlying factors of variation. During training, an encoder maps data into a latent distribution, and a decoder reconstructs the data from samples of that latent space. The training objective balances reconstruction quality with a regularization term that encourages the latent distribution to follow a known prior, typically a Gaussian. Generation then involves sampling from the prior and decoding. GAUs are conceptually elegant but sometimes produce blurrier outputs in image domains compared to other methods. Generative adversarial networks take a different approach. A generator network produces synthetic samples, while a discriminator network tries to distinguish real samples from generated ones. The generator is trained to fool the discriminator. This adversarial game can produce very sharp and realistic outputs, especially in image generation. However, GANs are notoriously difficult to train due to instability, mode collapse, and sensitivity to hyperparameters. Diffusion models represent a more recent and highly successful approach, particularly for image and audio generation. These models define a forward process that gradually adds noise to data until it becomes nearly pure noise. The model then learns the reverse process, step-by-step denoising that reconstructs structure from noise. Generation starts from random noise and applies the learned reverse process repeatedly. Diffusion models are computationally intensive but tend to produce high-quality and diverse outputs with stable training dynamics. Regardless of the specific model family, the training process for generative AI relies heavily on large datasets and large-scale optimization. Models typically contain millions or billions of parameters and are trained using variants of stochastic gradient descent. Automatic differentiation computes gradients efficiently through deep computational graphs. Training may take days or weeks on specialized hardware accelerators. An important practical detail in generative systems is sampling strategy. Even after a model has learned a probability distribution, the way we sample from that distribution strongly affects output quality. For example, in language generation, sampling directly from the full distribution may produce incoherent or overly random text. Techniques such as temperature scaling, top K sampling, and nucleus sampling modify the distribution to balance diversity and coherence. Lower temperature makes outputs more deterministic, higher temperature increases randomness. Prompting is another key component in modern generative AI workflows. Many generative models are conditional models, meaning they produce outputs conditioned on an input context. In text models, the prompt provides the initial context that shapes generation. In image models, conditioning may include text descriptions, class labels, or reference images. Prompt engineering has emerged as a practical skill for steering generative systems without retraining them. Fine-tuning and alignment are important post-training steps, especially for large language models. After pre-training on massive unlabeled corpora, models are often fine-tuned on curated datasets to improve helpfulness, safety, or task-specific performance. Reinforcement learning from human feedback is one widely used approach where human preferences guide the model toward more desirable outputs. This stage does not fundamentally change the generative mechanism but reshapes the output distribution. Another important concept is latent space structure. In many generative models, especially VAS and diffusion models, the model learns a continuous latent representation where nearby points correspond to similar outputs. This latent geometry enables interesting capabilities such as interpolation between samples, semantic editing, and style transfer. Understanding and controlling latent space remains an active research area. Generative AI systems must also address evaluation challenges. Unlike classification tasks where accuracy is straightforward to measure, generative quality is multifaceted. Metrics may assess likelihood, perceptual quality, diversity, or human preference. In practice, human evaluation often remains the gold standard, especially for open-ended generation tasks. Scaling plays a major role in modern generative AI. Empirical scaling laws show that increasing model size, dataset size, and compute often leads to predictable improvements. However, scaling also introduces engineering challenges such as distributed training, memory management, and inference cost. Efficient architectures, mixed precision training, and parallelization strategies are critical for practical deployment. Inference efficiency is especially important because generative models may be used interactively. Techniques such as quantization, caching intermediate computations, speculative decoding, and model distillation help reduce latency and cost. In diffusion models, researchers explore fewer denoising steps and better schedulers to accelerate sampling. Generative AI also raises important robustness and safety considerations. Because models learn from large datasets, they can reproduce biases, factual errors, or undesirable content present in the data. Mitigation strategies include dataset filtering, safety fine-tuning, output filtering, and controlled decoding. However, perfect control remains an open challenge. From a systems perspective, deploying generative AI involves more than model training. One must manage data pipelines, version models, monitor outputs, handle abuse prevention, and design user interfaces that set appropriate expectations. Observability and feedback loops are essential because generative models operate in open-ended spaces where failures may be subtle. Multimodal generative models are an increasingly important direction. These systems learn joint representations across text, images, audio, and video. Architecturally, they often combine modality-specific encoders with shared latent spaces or attention-based fusion layers. Multimodal generation enables applications such as text-to-image synthesis, image captioning, video generation, and cross-modal retrieval. Another frontier is controllability. Users often want precise control over style, content, or structure of generated outputs. Methods such as conditioning, guidance during sampling, adapter layers, and structured prompting aim to provide more reliable control without retraining the entire model. Energy and computational cost are becoming major considerations. Training large generative models can be extremely resource-intensive. Research into sparse architectures, mixture of experts routing, efficient attention mechanisms, and better training curricula aims to improve efficiency while maintaining performance. Conceptually, generative AI can be viewed as learning a compressed model of the world represented in data. The network parameters encode statistical regularities observed during training. Generation is essentially controlled sampling from this compressed knowledge. The remarkable capability of modern systems emerges not from explicit symbolic reasoning but from large-scale pattern learning combined with powerful architectures and optimization. Despite impressive progress, generative AI still has limitations. Models may hallucinate incorrect information, struggle with long-term consistency, or fail under distribution shifts. Understanding how to build systems that are more reliable, grounded, and interpretable remains an active research focus. What makes generative AI particularly transformative is its generality. The same underlying principles, large neural networks, gradient-based training, and probabilistic generation, apply across many modalities. As compute, data, and algorithms continue to improve, generative models are likely to become more capable, more efficient, and more deeply integrated into software systems. At its foundation, generative AI is about learning the structure of data distributions and using that knowledge to synthesize new examples. Everything else, architectures, training tricks, alignment methods, and deployment strategies, exists to make that core idea work at scale in the messy, high-dimensional reality of real-world data.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.